Welcome, scholars, to Mr. Honeycutt's math class. Today we're learning how to sketch sign charts from factored form. A sign chart is sort of it's a bridge between the graphical and the algebraics. They are super useful in calculus, which is why I want you to learn them now. It's one of those things that teachers might not teach you, but it's like most people who are using this stuff and doing this stuff know how to do it because it's so helpful and useful. But before we get to sign charts, we got to work on in behavior. So right now we're going to be, this video, we're determining in behavior from graphical or algebraic representations. All right, in behavior is basically what's the y value doing at infinities. All right, so the left in behavior is when it's going to the left of the graph. It's kind of like a birthday on a tombstone. It's when x is going to negative infinity. It's kind of, you can think of it as where the function comes from. And in limit notation, it's the limit as x approaches negative infinity of the function. The right in behavior, it's kind of like a death day on a tombstone. It's what's happening when x goes to positive infinity. It's where that function is going, the limit, and it's the limit as x approaches infinity of fx. So it's going, this is if I've got a graph, all right, the right in behavior is this one. The left in behavior is it's going here. So this is the positive infinity. This is the negative infinity. All right. What is the function doing as it's going in those directions? So in behaviors are usually one of these. Usually positive infinities, one. It's some number. That's as if there's a horizontal asymptote. Okay, here's another horizontal asymptote. Another thing is the in behavior might not exist. It might not ever like settle on something, whether that's positive infinity, negative infinity. We'll see some examples of those. Or it's negative infinity. So positive infinities kind of look like this. All right, negative infinities look like this. Or if we're going on the other end, it'll look like this. Okay. The zeros are going to be like a horizontal asymptote at the x-axis. And then some other number would be a horizontal asymptote at some other y value. So let's see what this looks like. So first we're starting, what's the left in behavior? The limit as it goes from the negative. Well, hey, look what's happening here. All right, well, that one's going to positive infinity. All right, this one here, well, what's happening over here? Well, that left in behavior, that's going to go to 0. All right, and all exponential functions, notice there's a horizontal asymptote at 0, so it's a y equals 0. And all exponential functions have this phenomena about them. So make sure, just because it's not a rational function, it can still have a horizontal asymptote, so watch out for exponentials. All right, what about this one, the left in behavior? Hey, look at this. Hey, this one's going to negative infinity. For most of these, we can assume there's an arrow here. Now, what about the right in behavior? All right, what's it happening as the limit is going to positive infinity? All right, well, what's happening here? Hey, that's also positive infinity. Hey, this one is also positive infinity. Hey, this one is also positive infinity. All right, let's look at some other ones. What other right in behaviors? Look at this one. This one's going to negative infinity. This one, notice it doesn't settle. So it's a does not exist. Okay, a D and E. Those of you who've watched Mean Girls, the limit does not exist. Now we're going to move on to, let's see if we can remember what these functions kind of look like. You can pause the video if you want. Now I'm going to sketch them. Okay, so x and even, hey, that looks like a parabola. And if it's negative, it's going to look like this. All right, an odd is going to look kind of like that. A negative odd would look like this. Honestly, that's how I remember the stuff that we're about to do next. I just know what these functions look like. I know that even functions basically are going to look like that. Negative x to an even power functions are going to look like this. Odd functions are going to look like this. X to the odd look like this. So remember, this is about the highest degree of a polynomial. Okay, so the highest power, if it's an even, it's going to look like this or this. If it's an odd exponent, it's going to look like this or this. Now let's look at this information in chart form. So the degree, all right, the degree would be the highest exponent. Okay, so in this case, the degree is 2, it's 6, over here it's 5, over here it's 7. Notice those are the highest exponents in these polynomials. When the degree is even, basically the right and left behaviors are going to be the same on these polynomials. So if it has a positive right end behavior, it's also going to have a positive left end behavior. All right, if their leading coefficient is negative, it's going to have a positive right end behavior and then also a negative left end behavior. If the degree is odd, okay, and it's a positive leading coefficient, it's going to have a positive right end behavior, but the odd degree tells us that the signs of the end behaviors are going to be different, okay, because they're different signs. So this is going to be a positive end behavior. That means this one's going to be a negative end behavior. However, if the leading coefficient is negative, that tells us the right end behavior is negative, but because the degree is odd, the end behavior is going to be, the left end behavior is going to be positive. Okay, and again, if you ever just forget all this stuff, just, hey, this looks like this one, okay, this is like this one, right, this is like this one, and this is like that one. Okay, so this is like a positive x squared, a negative x squared, a positive x cubed, a negative x cubed, right? Like, it's just, don't overcomplicate this, just learn what these all mean. But to review, when you're doing this algebraically, okay, what you're going to want to do is you're actually going to want to determine the right end behavior first. Okay, because it's going to be the easiest, because all you're going to do is use the sign of the leading coefficient. If the sign is positive, it's going to have positive right end behavior. If it's a negative sign on the leading coefficient, okay, that's the coefficient that goes with the highest exponent, okay, it's going to have a negative right end behavior. Okay, and then the second thing we're going to do is determine the left end behavior. We're going to use the even or oddness of the degree to determine if the sign is the same or different. If it's an even degree, it's going to have the same sign as the right end behavior. If it's an odd degree, it's going to have a different sign from the right end behavior. That's basically it. So use the right end behavior first. That's the one that's going to be most apparent from the sign, and then use the degree of the function, whether it's even or odd, to determine the left end behavior. Let's move along and try some. Make a little chart here where we're going to have the right end behavior. Okay, which would be the limit as x approaches positive infinity of f of x. And this would be the left end. Which is the limit as x approaches negative infinity for f of x. And I'll kind of write that on top. But all right, so again, we always start with the right end behavior. So, hey, what's the sign on the leading coefficient? Here's the leading coefficient. What's the sign? Well, the sign is positive, so it's going to be positive infinity. Okay? Now, and then is it even or odd? Well, it's even, so it's going to be the same. So it's also going to be positive infinity. Okay? Same. All right, now, let's do the next one. So here's my leading coefficient here. Is it positive or negative? It's positive, so this is going to be positive infinity. Now, there's no coefficient, or no exponent, excuse me, but it's implied. It's odd, so it's going to be different. So the left end behavior is going to be negative infinity. Notice the signs are different. And if you were to sketch the graph, it would look something like this. Hey, notice it keeps going to positive infinity on the right and to negative infinity on the left. Crazy. Same thing over here. My sign for the leading coefficient is negative, so that's going to go to negative infinity. However, it's to the first power, which is odd, so it's going to be a different sign, which means it's going to positive infinity. Now for this one, here's the leading coefficient. It's positive, so this one's going to positive infinity. But it's odd, so it's going to be different. So the left end behavior is going to be negative infinity. Over here, here's my leading coefficient. The sign on that leading coefficient is negative, so that one's going to go, the right end behavior is going to go to negative infinity. But because this is an even exponent, it's going to be the same. So the left end behavior is also going to go to negative infinity. Now I want to talk briefly about standard form versus factored form. These are two different ways we're often going to be encountering polynomials, and frankly, they're good for different uses. And that's why a lot of times in algebra, we want to kind of be able to jump between them. So that, for instance, in standard form, some things are really easy. Evaluating is pretty easy. Determining in behavior is really easy. Finding the y-intercepts, very easy often. And doing calculus procedures, you will see, is incredibly easy in standard form. What's hard in standard form, very hard, is finding x-intercepts, figuring out positive and negatives, and then even interpreting with calculus is tricky in standard form. Factored form, on the other hand, it's really easy to find x-intercepts, and then from there positive and negatives, and also to interpret for calculus. It's a little bit trickier to determine in behaviors and to evaluate. It's kind of tricky to find y-intercepts, and it is very, very tricky to do calculus procedures. So basically, you need to be able to jump between these forms. We're going to be working on that next class. But I just kind of want to show you where we're going with some of this. So, determining in behavior from factored form, we've got to figure out, all you got to do is just figure out the sign of the leading coefficient first, which is going to give you the right in behavior. And we're going to do that by multiplying our leading coefficients. So all I got to do is here for each term. So what's x times x squared? Well, that's going to be, the leading term would be x cubed. And then I got to check, make sure the sign, it still would be positive. So my right end behavior is going to be positive. So for that right end. And then because it's odd though, it's going to have a left end behavior of negative infinity. Okay. And we can also like figure out the sign from leading coefficient. We can add up the exponents as well. So like from here, here, and here. So hey, that's a 1, that's a 1, a 1. So hey, notice that sign there. So it's going to end up being like a negative x cubed. Can you see that? Negative x cubed. So the right end behavior is going to be negative infinity, but the left end behavior would be positive infinity. Okay? So it's going upwards. This one's going downwards. This one's going upwards, left, and then downwards to the right. So let's determine the end behavior on these. And these are, of course, a little bit trickier. But let's look at, so leading coefficients. Notice, hey, look at that, -2. Ooh, I've got a negative and a negative here. Ooh, so a negative times a negative times a negative. Well, that's going to end up being a negative. And then I've got 1, 2, 3. That's like a negative x cubed. So again, it's going to have, so the right end behavior, okay, which would be that limit as x approaches positive infinity of f of x is going to equal negative infinity, okay, because it's a negative x cubed. And then the left end, I'm not going to write the whole limit notation, but this one's the one that's going to go to positive infinity. Okay, so the function, all in all, is going to look something like this at the ends. Okay, and if it helps you to just kind of visually think like that, so this one's going to positive infinity on the left, negative infinity on the right. So here, on number 4, we don't have any negatives, so the whole thing's going to end up basically with the leading coefficient is going to be positive. Okay, notice we're only really concerned about the highest degree thing, just like for the horizontal asymptotes, because those are the only ones that really matter in the end. At the ends, not in the middles, but at the ends. So it's going to behave basically like this. Well, so the right end is going to be a positive infinity, and because it's even, there's no, the sign, that's because the right end, it's positive, no negatives here. And then because it's even, this is going to be the same, so the left end behavior is also going to be positive infinity. So the graph is going to look something like this at the ends. If I have like a same thing over here. All right. And that's it for determining in behavior from graphs and from algebra.